This is a demo of a Vivado Zync project running on a Zybo board. And we'll use Vivado to create the project, the IP, wire the IP together, export it over to the SDK, and then write a C program to blink these LEDs. So here's my Zybo board or Zybo board, and the 4 LEDs right here. Only 2 of them are lit up right now, and we'll see in a moment why that is. I'm going to open up the Vivado project. Once Vivado opens up, there's a navigator pane over on the left. And if we open up in the IP integrator, open block design and open the design here, after a few moments the block diagram appears. These are the IP blocks that were wired together with the IP integrator. And I won't go into the steps of creating these blocks in this video. I'll post a separate video that shows how they go all together. But 2 blocks. Let's look at the Zync processor, and then over here the GPIO block, which is responsible for driving the I/O pins on the Zybo board, allowing C to access the LEDs. If we open up this block, I've defined 4 GPIO points for the 4 LEDs. They're all outputs, and I set up the initial output value of A, which explains why alternating LEDs are lit up. That's what the A does. In the address editor, Vivado will automatically assign a address to the GPIO block, but our C program doesn't really need to access that address value directly. It turns out that Vivado will generate header files and populate structs, initialize structs, so that our C program can get access to the GPIO block without worrying about the actual address. Now if we go look at sources under constraints, there's a XDC file, a Xilinx device constraint file, that has a list of all the I/O points, mostly commented out, except for the 4 LEDs that I'll be accessing in this project. I didn't create this file myself. Instead, I downloaded it from Digilent's website for their Zybo board, and it can be found right here using the download link. Okay, now I'll export this Vivado project over to the SDK. I'll do a file, export hardware for SDK, accept most of the defaults here except for launch SDK, and this warns me that it'll override an existing export, which is fine. I'll click yes. After a few moments it opens and automatically compiles the project. This shows a C file that I've already created. And before we look at the code too much, why don't we download it to the FPGA board and watch it blink the LEDs, and then let's come back and look at some of the code that makes the LEDs blink. I go up to the Xilinx Tools menu and select Program FPGA. I'll accept the defaults here and do a program. So let's debug the project. First I'll set a breakpoint in a forever loop that blinks the LEDs. There I've set a breakpoint. Then I'll go up here and select debug. Runs the program up to main and then stops. So at this point if I click resume or run, it stops at that breakpoint. Over here the LEDs are off, And if I select step over, LEDs turn on. There's a bit of a delay in the video. And if I run again, it stops at the breakpoint, and if I step over again, then the LEDs turn off. Now let's take a closer look at some of the code behind the scenes responsible for blinking the LEDs. Essentially the code that closes the gap between the hardware side and the software side. There are a few include files like xparameters.h, automatically generated by Vivado when the hardware was exported to the SDK. But if we open it up, we'll find in here some addresses that we saw over on the hardware definition side, such as memory addresses for the GPIO. And fortunately, our code doesn't really need to reference those addresses directly. There's a more integrated or automated way for the C code to get these parameters from the hardware side. So looking at the C code, there's a call GPIO lookup config that uses a unique device ID generated by Vivado that gets me a data structure with configuration for the GPIO. One of the members is the base address. Another call, GPIO config initializes, essentially initializes an object. It's a struct that has parameters like the base address. Here's an assert statement to verify that the previous call was successful. Asserts will end up in an infinite loop or breakpoint if the assertion fails, if there's an error. Here's a call to set the direction of the I/O points. Here I'm passing in that GPIO object defined up here, and a couple of parameters that I defined here that defines our usage of the GPIO LEDs in this code. For example, a bit mask for the 4 LEDs and the LED channel, because a GPIO can accommodate up to 2 channels. And then in the forever loop, there's a call to GPIO discrete write that references the GPIO object, the channel of the GPIO, and then passes in data to write to the GPIO, essentially a mask of ones or a 0. The source code is posted on Google Drive in a zip file here, and I'll put a link in the video notes.